welcome you in the lecture series of random processes, detection and estimation. It is 17th lecture of this series. In the previous lecture, we have discussed about generalized matched filter. In this lecture, we will discuss about detection of deterministic signal with unknown parameters. And the outline of this lecture are: we will discuss the detection of sinusoidal with unknown amplitude. Also, we will discuss detection of sinusoidal with unknown amplitude and phase. And in the objective of this lecture, you will able to explain how to detect the sinusoidal signal when there is unknown parameter and or unknown phase. A problem is important when the signals are to be detected not completely known. The lack of signal knowledge may be due to uncertain propagation effect in the mobile radio or in the channel. For this problem, we will require advanced theory of composite hypothesis testing. The lack of signal knowledge results in degradation of the detection performance when compared with the optimal matched filter. For example, there is a sinusoidal signal Sn is equal to A cos 2 pi f naught n. In this, we may not know the value of the set parameter A, f naught, and phi. And we have discussed two main approaches in the composite hypothesis testing problem. These are generalized likelihood ratio test (GLRT). If the unknown parameters are modeled as deterministic, then we will use GLRT test. And if the unknown parameters are modeled as random variable, then we will use Bayesian approach. These two methods have different philosophy, so direct comparison cannot be possible here. Unknown amplitude. Let the deterministic signal Sn with unknown parameter, or you can say the amplitude A, and consider the two hypotheses. Hypothesis H0 corresponds to xn observed sample will be equal to omega n, means under hypothesis H0 there is no signal, only noise is present under hypothesis H0, and under hypothesis H1 xn is equal to A Sn plus omega n. Here Sn is known, but the amplitude of the signal Sn is unknown, and omega n is the white Gaussian noise with mean zero variance sigma square. And the problem is exactly we have discussed in the previous example 58, but in that case Sn was 1, is DC level, and of the unknown amplitude in white Gaussian noise. If the sign of amplitude A is known, then we will use optimal detector to produce the highest probability of detection for all values of unknown parameters for a given probability of detection. Optimal detector means NP detector. And if the sign of the amplitude A is not known, then we will use GLRT or Bayesian approach. So first we will use the optimal detector, NP detector. If there is NP detector, the GLRT decides likelihood ratio test decide H1 or H0 if the PDF under hypothesis H1 divided by PDF under hypothesis H0 means the likelihood ratio will be greater than or less than threshold value gamma, and the PDF under hypothesis H1 it will be 1 by 2 pi to the power n by 2 into 1 by sigma to the power n e to the power minus 1 by 2 sigma square summation n0 to n minus 1 xn minus asn whole square, and divided by the PDF under hypothesis H0 it will be 1 by 2 pi to the power n by 2 into 1 by sigma to the power n e to the power minus 1 by 2 sigma square summation n0 to n minus 1 x square n, and it will be greater than less than threshold value gamma. So taking natural log of both sides, you will get 1 by 2 sigma square summation n0 to n minus 1 minus 2a Sn xn plus a square s square n greater than less than log e gamma, and consider this is equation first. Or I can write this equation first as a summation n0 to n minus 1 x n Sn greater than less than sigma square log e gamma plus a square by 2 n0 to n minus 1 s square n, and we have put this term in right side because it is not involving the component of the observed signal as xn. So now if we consider this total value as the new threshold gamma dash, and if a greater than 0, then the NP test decide h1 or h0. If the test statistic means equal to summation n0 to n minus 1 xn Sn greater than less than gamma dash by a, this is new threshold value gamma double dash. And if a less than 0, then NP test decide h1 or h0 if the test statistic summation n0 to n minus 1 x and Sn greater than less than gamma dash. In both cases, you can see in the when a greater than 0, test statistic will give the hypothesis h1 if this is greater than threshold value gamma double dash. But in this case, when a less than 0, test statistic will decide in favor of h0 when the test statistic greater than the threshold value gamma dash. So we cannot have the unique test. So if a sign of a is unknown, we cannot construct a unique test, and the poor result would be. And if a less than 0, then the expected value of the test statistic, it will be expected value summation n0 to n minus 1 x and Sn, and it will be a summation n0 to n minus 1 s square n. So if it will be less than 0, so the test does not exist here. And in this case, the probability of detection, it is q inverse pf minus d square. D square is the deflection coefficient, and it is a summation n0 to n minus 1 s square n by sigma square, and this is epsilon by sigma square. So here you can see that it is less than 0. So the probability of detection will not give the valid result here, in this case when a less than 0. So when the amplitude is unknown, we must use the GLRT or Bayesian approach. Now we'll consider GLRT test. GLRT decide h1 or h0 if the PDF under hypothesis h1, which includes the estimated value of unknown amplitude a, divide by PDF under hypothesis h0, means the likelihood ratio, GLRT, general likelihood ratio test, it will be greater than less than threshold value gamma. Here a is the maximum likelihood estimate of a under hypothesis h1, and it will be expected value of a, it will be summation n0 to n minus 1 x and Sn divided by n0 to n minus 1 s square n, and it comes from if you have considered the equation first of slide number 6 and taking the differentiation of the log likelihood function, then you will get 2 n0 to n minus 1 Sn xn is equal to 2a n0 to sigma n0 to n minus 1 s square n. So it is from equation first from slide number 6. So after taking the differentiation of log likelihood function with respect to a and putting it to 0, then you will get this equation, and the expected value from this equation, it will be summation n0 to n minus 1 x and Sn divided by n0 to n minus 1 s square n. So you can write here the log likelihood ratio, it will be 1 by 2 sigma square summation n 0 to n minus 1 minus 2 expected value of a Sn xn plus expected value of a square s square n greater than less than log e gamma, or I can write it as minus 1 by 2 sigma square minus 2a expected value of a into expected value of a summation n 0 to n minus 1 s square n plus expected value of a square summation n 0 to n minus 1 s square n greater than less than log e. And this is because the expected value of a is summation n 0 to n minus 1 x and sn divided by n 0 to n minus 1 s square n. So from this you will get summation n 0 to n minus 1 x and sn. It will be equal to expected value of a as summation n 0 to n minus 1 s square n. So after putting this, you will get this expression a cap summation n 0 to n minus 1 s square n. So finally we decide h1 or h0 if a cap square greater than less than 2 sigma square log e gamma divided by summation n 0 to n minus 1 s square n, or you can say the mode of the estimated value of unknown parameter or unknown amplitude greater than less than under root 2 sigma square log e divided by summation n 0 to n minus 1 s square n. For noise only, we expect a should be expected value of a will be 0, and when the signal is present, the mode of the expected value should depart from the 0. So now the test statistic, it will be summation n 0 to n minus 1 xn sn whole square greater than less than 2 sigma square log e gamma n 0 to summation n 0 to n minus 1 s square n. And this test statistic, because the expected value of a, it is summation n 0 to n minus 1 xn sn divided by summation n 0 to n minus 1 s square n. And we decided h1 or h0 if a cap square greater than 2 sigma square log e gamma divided by summation n 0 to n minus 1 s square n, as you have seen in the previous slide. So from here the test statistic, it will be a cap square. This means summation n 0 to n minus 1 xn sn whole square greater than less than 2 sigma square log e gamma into summation n 0 to n minus 1 s square n, because we are taking the square of the a cap, so it will be here whole square here, and it will be a cap whole square. When putting the value this, you will get this test statistic. So, and you can write this is the new threshold value, or you can write this test statistic as the mode of summation n 0 to n minus 1 xn sn. It will be less than equal to under root 2 sigma square log e gamma summation n 0 to n minus 1 s square n, or I can write it as under root gamma dash new threshold value. Now the detector is just a correlator that accounts for the unknown sign for a by taking the absolute value. So, and the block diagram of the GLRT for unknown amplitude, it will be, this is the test statistic. So first of all you have to find out Sn combination of xn and Sn, then you will get the summation of Sn xn summation n 0 to n minus 1, and after taking the whole square of this summation, then you will get this test statistic, and to compare this test statistic with the threshold value gamma dash, and if it is greater than, then we will decide hypothesis H1, and if it is less than gamma dash, then we will decide in favor of hypothesis H0. And here let this mode of summation n0 to n minus 1 x and Sn is ux. So you can see the ux means summation n0 to n minus 1 x and Sn will have the normal distribution with mean 0 and variance sigma square summation n0 to n minus 1 s square n under hypothesis H0, and under hypothesis H1 it will be the normal random variable with mean a into summation n0 to n minus 1 s square n, and with variance sigma square summation n0 to n minus 1 s square n. And the probability of false alarm, it will be the probability of mode of ux greater than and root of gamma dash when h0 is true. So I can write this as probability of ux greater than gamma dash under hypothesis h0 plus the probability of ux less than minus under root gamma dash, because there is more. So we have taken two values under root gamma dash and minus under root gamma dash under hypothesis h0. So we can find for this probability part, it will be q under root gamma dash divided by under root sigma square summation n0 to n minus 1 s square n plus 1 minus q function of minus under root gamma dash divided by under root sigma square summation n0 to n minus 1 s square n. Or I can write this as 2q function of under root gamma dash divided by under root sigma square summation n0 to n minus 1 s square n. And the probability of detection, it will be q inverse probability of false alarm divided by 2 minus under root epsilon by sigma square plus q inverse pf by 2 plus under root summation under root epsilon by sigma square. And here this is the deflection coefficient epsilon by sigma square. So the probability of detection, it will be q inverse pf by 2 minus under root d square plus q inverse pf by 2 plus d square. D square is the deflection coefficient, and d square is here a square summation n0 to n minus 1 s square n by sigma square, and it is epsilon by sigma square. Epsilon is the energy of the signal and sigma square is the variance of the noise. Now the sinusoidal detection. The detection of sinusoidal in white Gaussian noise is a common problem in many fields like radar, sonar, communication system. So let the two hypotheses, H0 hypothesis corresponds to xn is equal to omega n, where omega n is the noise. So under hypothesis H0 there is only noise, and under hypothesis H1 the xn is a cos 2 pi f0 n plus phi plus omega n. Here in place of Sn, the signal is in the cos form, a cos 2 pi f0 n plus phi, and where omega n is the white Gaussian noise with zero mean variance sigma square, and the parameters a f0 phi may be unknown. Here the unknown parameters are deterministic. Our approach will now be the use of GLRT for the following cases: when a is unknown, only a is unknown, and when a and phi both are unknown, and when a phi f0 are unknown, and when a phi f0 and n0 means time delay is unknown. We will discuss these two in this lecture, and these two will be discussed in the next lecture. So now first we will discuss the unknown amplitude. Let the two hypotheses, and we are not including here the delay n0, time delay n0. So with the hypothesis h0, xn is omega n, only noise is present with under hypothesis h0, and under hypothesis h1 xn is a cos 2 pi f naught n plus phi plus omega n, where Sn is cos 2 pi f naught n plus phi is known and amplitude A is unknown. So we can see we decide h1 or h naught from the previous slide. We know the test statistic summation n0 to n minus 1 x and Sn whole square greater than less than threshold value gamma, or the sign of the amplitude is unknown here. So I can apply this Sn here. Sn is a cos 2 pi n plus phi. So the test statistic, it will be summation n 0 to n minus 1 xn cos 2 pi f naught n plus phi whole square greater than less than gamma dash. And the expected value of A, it will be summation n0 to n minus 1 x and Sn. Here Sn is cos 2 pi f naught n plus phi divided by summation n0 to n minus 1 s square, and means cos square 2 pi f naught n plus phi. And the approximated value of this 2 by n summation n0 to n minus 1 x n cos 2 pi f naught n plus phi, because from the previous slide you know the expected value of A, it is summation n0 to n minus 1 xn Sn divided by summation n0 to n minus 1 s square n. This is the maximum likelihood estimated value of A, and here Sn is cos 2 pi f naught n plus phi. Now you know the test statistic, it is Tx is equal to summation n0 to n minus 1 xn cos 2 pi f naught n plus phi. So first of all we will combine xn and cos 2 pi f naught, and the block diagram for the GLRT for sinusoidal detection with unknown parameter, it will be, we will combine first xn and cos 2 pi f naught and phi, then take the summation of this and taking the whole square, because the test statistic is the whole square of this value, then taking the whole square of this summation and compare this test statistic here, compare this test statistic with the threshold value gamma dash, and we will decide whether h1 or h0 is true. And here this is the test statistic. Then the probability of false alarm, it will be q function of under root gamma dash divided by sigma square summation n0 to n minus 1 cos square 2 pi f naught n plus phi, or you can say the probability of detection, it will be q inverse pf by 2 minus d square plus q function of q inverse pf by 2 minus d square. D square is the deflection coefficient, and it is a square summation n0 to n minus 1 cos square 2 pi f naught n plus phi by sigma square, and it is epsilon by sigma square, or you can say it is n a square by 2 sigma square. Now the sinusoidal detection with unknown amplitude and phase. When amplitude A and phase are unknown, we must assume that A greater than 0, otherwise two different sets give the same signal and the parameters will not be identifiable. So the GLRT decides h1 or h0 if the PDF under hypothesis h1 with estimated value of amplitude A and phase, and divided by the PDF under hypothesis h0. So this is the generalized likelihood ratio, and it will be greater than less than threshold value gamma, where A and phi are the maximum likelihood estimated value and f0 is near between 0 to 1 by 2. So we decide h1 or h0 if the likelihood ratio, it will be 1 by 2 pi to the power n by 2 into 1 by sigma is to the power n into is to the power minus 2 sigma square summation n0 to n minus 1 xn minus estimated value of a cap cos 2 pi f naught n plus phi cap, the estimated value of the phase and the whole square of this total term, divided by 1 by 2 pi to the power n by 2 into 1 by sigma to the power n into e to the power minus 1 by 2 sigma square summation n 0 to n minus 1 x square n, and this total likelihood ratio, it will be greater than less than some threshold value gamma, and put this equation as equation first. If alpha 1, we consider alpha 1 is cos a cos phi and alpha 2 is minus a sin phi, then the estimated value of alpha 1 cap will be equal to 2 by n summation n0 to n minus 1 xn cos 2 pi f naught n, and estimated value of alpha 2 cap it will be 1 by 2 by n summation n0 to n minus 1 xn sin 2 pi f naught n. So for this case, for large n, we will get the estimated value of a, it will be under root estimated value of alpha square plus estimated value of alpha 2 square, and the estimated value of phi, it will be tan inverse minus estimated value of alpha 2 divided by estimated value of alpha 1. Here because you have the signal Sn is a cos 2 pi f naught n plus phi, so after taking it as cos a plus b, cos a cos b minus sin a sin b, so you have separated all the parts and given the value of alpha 1 a cos phi and alpha 2 a sin phi, then you will get these estimated value of a and estimated value of phi here. So again, take the equation first. Likelihood ratio, it is equal to 1 by 2 pi to the power n by 2 into 1 by sigma to the power n e to the power minus 1 by 2 sigma square summation n0 to n minus 1 xn minus estimated value of a cos 2 pi f naught n plus phi estimated value of phi and whole square of this term xn to this value, and divided by 1 by 2 pi to the power n by 2 into 1 by sigma to the power n into e to the power minus 1 by 2 sigma square summation n0 to n minus 1 x square n, and this likelihood ratio will be greater than or less than some threshold value of gamma. So taking natural log of this likelihood ratio, the log likelihood ratio, it will be log e lx, it will be 1 by minus 1 by 2 sigma square into summation n0 to n minus 1 minus 2 xn estimated value of a cos 2 pi f naught n plus estimated value of phi and plus summation n0 to n minus 1 estimated value of a square cos square 2 pi f naught n plus phi. Since you know summation n0 to n minus 1 xn a cap cos 2 pi f naught n plus phi, so after this applying cos a plus b, cos a cos b minus sin a sin b, so you will get the expression as summation n0 to n minus 1 xn cos 2 pi f naught n into expected value of a into cos phi minus summation n0 to n minus 1 xn x sin 2 pi f naught n expected value of a cap sin phi expected value of phi. So here is also expected value phi. Now it will be equal to n by 2 alpha 1 cap plus alpha 2 cap. Since summation n0 to n minus 1 cos square 2 pi f naught n plus phi, it is approximately n by 2. And put this equation and first and second, and the log likelihood ratio, it will be log ELX. Now it will be minus 1 by 2 sigma square minus 2 n by 2 alpha 1 cap square plus alpha 2 cap square plus n by 2 a cap square. And I can write this expression as minus 1 by 2 sigma square minus n by 2 alpha 1 cap square plus alpha 2 cap square, and it will be equal to n by 4 sigma square alpha 1 cap square plus alpha 2 cap square. So we decide h1 or h0 if this value log likelihood function n by 4 sigma square into alpha 1 cap square plus alpha 2 cap square, this log likelihood function which we have estimated, which we have calculated here, and it will be greater than less than equal log E gamma. But alpha 1 cap square plus alpha 2 cap square, it will be 2 by n whole square into summation n0 to n minus 1 xn cos 2 pi f naught n whole square plus summation n0 to n minus 1 xn sin 2 pi f naught n whole square. And you can calculate this as 4 by n into 1 by n summation n0 to n minus 1 xn is to the power minus j2 pi f naught n whole square of this term, and you will get 4 by n I f naught, where I f naught, it is this term, I f naught is this term, and I f naught is the periodogram evaluated at f is equal to f naught. So we decide h1 or h0 if n by 4 sigma square alpha 1 cap square plus alpha 2 cap square means the log likelihood function, it will be greater than less than log E gamma, or I can write it as, because you have calculated alpha 1 cap square plus alpha 2 cap square, here 4 by n I f naught. So here it will be, I can write it as I f naught greater than less than sigma square log E gamma. I f naught is the periodogram, so we will compare the periodogram with the threshold value sigma square log E gamma. This is the new threshold value, sigma square E gamma is equal to gamma dash. This detector and this form of detector is identical to the Rayleigh-Frading model. And now the GLRT for the sinusoidal detection with unknown amplitude and phase. The block diagram for this, it will be the IF naught periodogram, that is summation n0 to n minus 1 xn is to the power minus j 2 pi f naught n and whole square of this term, or in the cos or sine form you can write it as summation n0 to n minus 1 xn cos 2 pi f naught n whole square plus summation n0 to n minus 1 xn sine 2 pi f naught n whole square of this term. So to find the periodogram or test statistic, first of all we will combine xn cos 2 pi f naught n and take the summation from 0 to n minus 1 and taking the square of this total term, and also we will combine separately xn sine 2 pi f naught n and summation, take the summation of this term from n0 to n minus 1 and take the whole square of this total calculated value. So from this equation the block diagram will be, first we have taken xn and it is combined with cos 2 pi f naught n and sine 2 pi f naught n separately. Then we'll take the summation n0 to n minus 1 of this combined term and then take the whole square of this total term, and it will be the combination of these two. It will be the periodogram, and then this periodogram is compared to the threshold value, whether it is greater than or less than the threshold value. And if this periodogram is greater than the threshold value, then you will decide H1, or less than threshold value, then you will decide H0. Or in exponential form, the block diagram can be represented as take the xn and exponential e to the power minus j 2 pi f naught n, which involves both sine parameter and cos, and take the summation and take the whole square of this total term, and we will get the periodogram and compare this periodogram with the likelihood ratio, and then compare this periodogram with the threshold value. If this is greater than threshold value, then you will decide the hypothesis H1, and less than threshold value, then you will decide H0. This detector is also known as incoherent or quadrature matched filter. So alpha is here are alpha 1 plus alpha 2, and alpha is the normal distribution with mean 0 and variance sigma square 2 into identity matrix I under hypothesis H0, and under hypothesis H1 it will be the normal distribution with mean value with the matrix under root n by 2 cos a cos phi and minus under root n by 2 a sin phi, and with variance sigma square and identity matrix I. In this case, probability of false alarm, it will be e to the power minus gamma dash by sigma square. You can calculate this, and probability of detection q x2 dash square lambda q function of this log q function of 2 log e 1 by pf, where lambda is na square by 2 sigma square, and here this q x2 dash square lambda, it is integration x to infinity dt dt, and x2 dash is a random variable. It is also possible to use Bayesian approach to detect a sinusoidal with unknown amplitude and phase. Here only we have considered the GLRT test. You can also use the Bayesian approach for the detection of this type of detection where there are unknown amplitude and phase. So far in this lecture, we have discussed about detection of deterministic signal with unknown amplitude and phase. This was 17th lecture of the lecture series of random processes, detection and estimation. In the next lecture, we will discuss about detection of deterministic signal with unknown amplitude, phase, frequency and delay time. Till then, thanks for listening this lecture. Thank you.